good to go.
Okay, now it's working okay? Okay, so thank you very much to all of you for coming here, and I would like to thank the organizers, of course, Joachim and Francesco and all of the others who invited me to come here. And since this is a little bit of an interdisciplinary community, I'll try to go through a few concepts which would sort of introduce the whole thing. The introductions will not be too long, and basically I'll mention a few topics which sort of overlaps with the questions which were in there. Okay, so let me try to go like this. Okay.
There's a pointer leaning up against the blackboard.
Okay, we have a non-digital pointer. Okay, let me just introduce the Projector Monte Carlo and fixed node approximation, so that we know what we are talking about. So basically, what is QMC? We basically try to project out from reasonable trial wave function, and I will say later what is reasonable, the ground state of the given symmetry by applying this projector. Okay, that tau is a real parameter or imaginary time, and basically it's not too difficult to show that then it corresponds to the stationary solution of the Schrodinger equation. One difference with the usual, say, basis set expansions or those types of methods is that this is solved stochastically. Basically, you sample the solution. It's represented by a sum of delta functions, and you evolve those delta functions in the 3n dimensional space. Of course, we know that there is a fundamental difficulty in there. That there is a Fermion sign problem, so that it's difficult to or impossible to sample distributions which are not positive everywhere. And most of this talk will actually talk about the fixed node approximation, which tells you the following. If you have a reasonable approximation to your ground state, it has a sign structure if the wave function is real. And wave function is always can be chosen real if the Hamiltonian is time reversal symmetric. If it is not time reversal symmetric, but it's still a stationary state, you can generalize it to fixed phase. But nevertheless, for the time being, we can just talk about the real wave function. If it is, of course, the real wave function is obvious. If I have two particles, two fermions here, and I do this, I go to minus exactly the same value. So if I try to go back and I watch the wave function, suddenly here I hit the zero. That zero is a part of the fermion node, which is basically defined by this implicit equation. In general, if you have n particles in three-dimensional space, it's a 3n minus 1 dimensional hypersurface, which divides the configurations of the quantum particles into domains of constant wave function sign, if we have real wave functions, pluses and minuses. Now, obviously, the accuracy will be determined by the accuracy of the nodes which you have in the beginning. One thing is that if you have an exact node, if you happen to be able to do that, you would get an exact energy in polynomial time with some caveats, and I don't want to go into caveats for the time being. But otherwise, if you don't have it exact, there will be something which we can call fixed node bias. Basically, that would determine your accuracy. Now, this looks very complicated. It actually looks much more complicated than the Schrodinger equation. Who knows what to do with the 3n minus 1 dimensional hypersurface? Still, I will try to convince you actually over the course of the talk that in many cases it is very accurate. Sometimes it is the most accurate method which you have. And the method which I will be mainly using under the acronyms of DMC is the diffusion Monte Carlo, which basically just recasts this projection into a particular form, or fixed node diffusion Monte Carlo, basically where I will be emphasizing that approximation. Okay, mostly I will be talking about the electronic structure types of applications, molecules, atoms, solids, those types of things. So our Hamiltonian is basically valence electrons only. The cores will eliminate with effective core potentials, and I don't want to go into details. It's a methodology which is technically complicated, but reasonably well understood and used. Explicit electron-electron interactions, continuous space, basically the original definition of the Hamiltonian. About the trial wave function, a few words. Well, we want to describe the correct electronic phase, insulator, metal, or whatever. It will be explicitly correlated, and we also want it to be possible to sample it efficiently. One could invent a variety of interesting wave functions which are as difficult to sample as would be the original solution of the many-body problem. So the most commonly used form which is used in this field is correlated Slater or Jastrow, either in single configuration or multi-reference. And this is built up on, say, Hartree-Fock one-particle state, density functional one-particle states, or even more elaborated one-particle states. For example, you can take natural orbitals from some configuration expansion. So this is with the single reference, and this is with with multi-references. Now here I divided this into determinant of spin up and determinant of spin down, which is a little bit departure of a standard Hartree-Fock thing. Note that if the Hamiltonian doesn't have any spin-dependent term, and I will talk about the generalization later, but if it doesn't have any spin term, which is of course often not the case in nuclear physics, but here very often it doesn't, at least in the first 3 rows of the periodic table, then all the spins and all the S squares, individual or total, commute with the Hamiltonian. Therefore, they are preserved quantum numbers. Therefore, you can assign the spins in the beginning according to the spin state, and therefore they become labels. Once they become labels, the big Slater determinant factorizes into product of 2. Okay. Yeah, the correlations, well, let's put it this way, I consider that, well, here what I put explicit 2 or 3 particle correlations. So you put some correlation functions in there, expand it into appropriate basis, and typically what you end up, few parameter things are reasonable. Once you put more and more parameters, it becomes going into diminishing returns. Basically, you don't get any improvement because you don't have a right functional form. So this includes, say, pair correlations between the electrons. So you can describe electron-electron cusp, which corresponds to the divergence of the Coulomb interaction. And what we do is very often put a 3 particle correlations, namely electron, electron, ion, which are the next most important, after the pair correlations. So this is expanded into some particular basis, some Pade functions, or something like that. There are actually a number of forms used, and that is optimized in the variational Monte Carlo, basically minimizing the energy or minimizing the variance. I was going too fast through that, so maybe that was too fast. Anyway, because I wanted to get into the interesting stuff. Now the fixed node approximation, let me come back again so that we understand what's going on here. This is a very interesting and actually a little bit of a leap of faith here, because we replace the anti-symmetry, which is perfectly non-local. I mean, this part of the wave function is perfectly represented with this type of a wave function, although we made a big move in the configuration space. So we replace it by something which is really local, and it's a boundary. And it's very easy to enforce the boundary in the evolution of the delta functions in the configuration space, because basically you are either on one side of the boundary or on the other side of the boundary, and you always know where it is. I mean, it looks scary in the beginning because, I mean, this is a sample of a solid calculation. This is a solid supercell. These are wave function values, and these green sort of a complicated 3-dimensional landscape. And this is just the 3-dimensional subset of the 59-dimensional node. Looks impossible to handle in any other way, but actually it's handled implicitly. You just write the determinant of more complicated antisymmetric function. What is interesting is that approximate nodes are actually often surprisingly accurate. Let me give you an example of this. And so this is a typical what you would do in a condensate matter physics. And I just have chosen this example because it was kind of an interesting case. If you take iron oxide solid, transition metal oxides are very complicated materials because they can show almost any quantum phases which you can think of. You can have metal, you can have insulator, you have superconductor, you have ferroelectrics, you have mixtures of multiferroics and whatever. Basically, those systems have very complicated possibilities, and it's because you have a competition of Coulomb exchange, correlation, and crystal field effects. And there are many possibilities which can happen. It's very often you end up with open D shell, and there's iron oxide. It has a relevance for high pressure physics because a large part of the Earth interior is actually iron oxide doped with other elements at various pressures and temperatures. And I didn't mention too much about the density functional, but I hope that you at least have a perfunctory knowledge of that thing. That is a mainstream method in this field, and basically what you can, if you just take the basic methods in there, you will get a metal, although in reality it's a large gap insulator, so you get wrong electronic phase, and actually you get even wrong equilibrium atomic structure. You get a high pressure structure as lowest instead of this one, which is a usual antiferromagnet, basically of NaCl.
When you say something is wrong, is that because it's experimentally known?
Yes, this is basically because experimentally known, but not only. I will try to convince you that we now even theoretically know that it is actually a large gap insulator. So I'm saying that, well, this is the usual, condensate matter parallels. If it doesn't agree with the experiment, you say it's wrong. So, so in that sense, that's correct. But I will try to convince you. Yeah, sure.
Here you talked about the electrons all the time, but you didn't mention the nuclei. So you're going to change their positions as well during this process?
Okay, so in this case, I will be doing something because we'll be looking at the equation of state, namely the dependence of energy on a pressure. So I'll be changing the positions of the atoms, but in a special way, namely to the compression. Yes, one can do it, except that it's very expensive in these types of methods, and I'll be mentioning that later. Pairing. Yes.
Now, pairing means phonons, and that means nuclei have to vibrate in order to have the.
Oh,
so
okay. Okay. Wow. If you think about the vibrations and the typical electronic energies.
You'll need the phonons in order to do the pairing.
Okay, but we are still far away from that, because if we could do this, we would be doing superconductors instantly.
No, I understand.
The trouble is that the resolution, I haven't gotten even to the point to show the resolution which we can get. Basically, the resolution which we can get, because we are taking a lot of chemistry in a very honest and straightforward way into the whole thing. And it's a huge baggage, because simply the energy scale is of the order of hundreds of electron volts, and we are looking at the resolution of about 1/10 of an electron volt, and phonons are about 10 millivolts or so. Yeah. So we are roughly 2 orders of magnitude still off. We might have a superconductor in the machine, but we will not know it because we don't have a resolution to say that. Okay. So in that sense, but I'll be going through those things in a moment. So just to give you an idea what happens. So basically, these are if I take DFT and take hybrid functions which mix the exact exchange. Just in order to get to some reasonable agreement with the experiment, you have to fiddle with the parameters in there, which are very difficult to get in any self-consistent way. Basically, you have a lever which you can change. It will be a mixing of the Hartree-Fock or using Hubbard-U or other corrections. So if I put here 10% of the Hartree-Fock into DFT, I get 7 GPa transition, and now it is correct because the slope is positive in this sense, and I see B1 as a lower one. If I put 20% of the Hartree-Fock into the density function, I get 43 GPa, and I'm still not where I need to be if I say the experiment is my validation. gigapascals, yeah. So, and basically there is no obvious reason why I should choose this type of, this value of the weight, which would be 10% or 20%, or whether I should crank Hubbard-U or whatever.
My recollection is the chemists like 50%. Is that?
Not really. Chemists like 20%. Actually, I will give a justification why it comes 20 in a second. So. Okay, so let's just give a landscape where we are. So take iron solid. This is the DFT column. This is the fixed node DMC column, and this is the experiment. Here is the difference between the high pressure and the low pressure. And here you get minus 0.2. In reality, you don't see the other phase at ambient pressures. We get about half an electron volt with the error bar of about 0.1. That's per formula cell, okay, per primitive cell. Now cohesion, you get roughly 11 electron volts. DFT people are fine with it because they know that it overbinds a little bit using the standard formulation. In experiment, it's roughly this one. This is a little bit too good. There is a cancellation of errors. I wouldn't say that it should come out that well, but it is always very reasonable. Okay. Now the equilibrium constant. So we changed the whole thing, but not changing the structure, only changing the lattice constant. We are getting pretty close to the whole thing, and this is also pretty nice. There is a bulk modulus, which is reasonable too. We get also a gap. You see here you have a metal, and the gap is not that great, but it's reasonable also. How do you get a gap? Because you understand, we are calculating only one energy, and that's the total energy. So I have a supercell, I feed it with electrons, put about 200 valence electrons in there, and I look what is the gap. So I need to create an excited state, very much like in nature. When you hit it with a photon, you create an excited state. Basically, you take the top valence electrons and you put it, say, somewhere in the conduction band into a particle state. You get another total energy, you calculate it, you subtract the two energies, and you get a gap, very much like in nature. So there are no one particle values here, no one particle eigenvalues, nothing like that. You really do what the nature does. It knows only one energy, and that's the total energy. You have one, you hit it, you go into the excited state, exactly in here.
Is that
yes?
the unique way to do it?
That's not the only way, but that's one way how to do that.
But your wavefunction is based on DFT. And for DFT is gas. So the band is gapless, right? Because
no, there is no. The DFT shows you one particle eigenvalues. If you feed those these orbitals into the whole thing.
No doubt, you know the metal insulator band theory.
Oh yeah, yeah, sure. So you know the right bands.
You say that you open a gap even though.
Exactly. You absolutely.
Is represent the metal.
Sure. Because this is. You know, this is not the.
This is a real multi-insulator.
Absolutely. And you get it because you are using variational method, unlike the DFT, which has an effective potential.
It's interesting that one can doubt about how you can control the size effect. Because in DFT you have to do the K average.
Sure, you do the K average here as well. It's basically the same type of thing. The fact that the wave function, it's a many-body object, there's a different energy than one particle eigenvalues from an effective theory is not that surprising. Anyway, let's. Yes. Yes. Okay. So once we can calculate the energies, we can calculate the energies dependence on the volume, and you can then construct actually. So this is essentially the one for the equilibrium phase. This is for the high pressure phase. Then you can put it on a PV diagram and compare with the experiment. So these are our predictions in here, we are not completely sitting on the experiment, which is okay, because we have ideal iron oxide. In experiments, you never have ideal iron oxide. It doesn't want to be stoichiometric for iron oxide, so there's always a little bit less oxygen than it is usually. And the experiments were between 70 to 100 GPAs for this transition. We see about 65 GPa for the transition, which I consider to be very satisfactory, considering there is no, as I said, a human hand didn't touch these calculations. I just put the basic formulation into the machine, pushed the button, got the numbers, plotted it out, and this is what came out. So in that sense, we now, or we have a reasonable, we have a reasonable results to say that this is a large gap insulator. It has a transition roughly at this pressure, and it corresponds very reasonably to the experimental situation. It's not perfect in any means, but it's very reasonable.
What's the red and blue on the left?
Which one? Oh, I'm sorry.
Yeah.
Which one? This is the equilibrium, and that's the high pressure. Here?
Yeah.
So this is one EV curve, and this is another EV curve. And so here is the double tangent construction to get the pressure when it transits.
Sorry, what's the one?
Energy is a function of volume.
For two different structures.
For two different, yeah, this is the equilibrium structure, and this is the high pressure structure. I was not clear, I'm sorry. And here it's plotted the same thing with PV, basically taking enthalpy and at zero temperature having glucose. Okay, now, there was an interesting component in this calculation which I didn't explain so far, and that was the one, what were the orbitals which we are using? And Sandro already pointed out these were probably DFT orbitals. These were DFT orbitals, but a little bit educated DFT orbitals, okay? How the education has happened. So I take a functional and I mix into exact Hartree-Fock, so you get a hybrid functional. Of course, it's very easy to fiddle with the weight, and you can change the gaps and various things. And actually, what you can produce in that way, set of orbitals which is parameterized by this weight. Okay, so I have said for this weight, this value, that value, and so on. So I tried to change the weight. This is the weight here. And I looked at the total energy, fixed node DMC energy, which I get. And you get a very nice curve, like this, which has a clear minimum. Namely, there is an optimal weight as far as the fixed node approximation is concerned. Basically, there is an optimal effective one-particle Hamiltonian which gives you the optimal nodes. And that mixing is actually at the 20% roughly, which is exactly what chemists claim that this is right, because you get it in the first order perturbation theory. If you try MP2 or something like that, you get roughly 20 to 25%. And this is actually, you see, this is the error bar, so anywhere within that thing, it's okay. So whether this is 15%, 20, or 25, it doesn't matter. As far, we don't have a better resolution. That's the best.
This is a single determinant. Right?
This is a single determinant, and it's an antiferromagnetic insulator. So it's pretty interesting, actually. And what happens in here? Yes.
Breaking the symmetry.
Yeah, I'm breaking the symmetry.
So the DFT has a gap.
No. No.
No.
Well, with the mixing, of course. With the mixing, yes. Here, once you mix 20%, it is a clear gap. Absolutely. Absolutely.
You don't change the problem.
Right. But even, Sandro, even if you would feed the ones which don't come, well, actually, if you if you spin polarized, you get it. Yeah. Okay.
Make the way stochastic too.
Pardon?
Can make the way stochastic too.
Sure.
So would that help or not?
Not much. Sure, one can do all kinds of stuff. Big, sure. Oh yeah, I mean it would converge in there. The more interesting thing would be if you would take weight for each particular set of orbitals of a given symmetry different, then you get into a much more interesting stuff, but a huge optimization problem. And that's a big big issue because you are, this is a stochastic picture, so the error bar, it's always a question how much you want to invest into the optimization within a given error bar and how costly it is actually to go down with it. Now what you see is here, if you change this weight, you go from the Hartree-Fock into which wants to be very ionic, to DFT, which wants to be much more smooth and much closer to the covalent sort of a picture. And note that this is actually a cool thing. We use this as a variational theory to optimize effective one-particle Hamiltonian. Okay? Because otherwise you have no idea why it should be exactly 20%. So we know why it should be exactly 20%. This gives you the best possible nodes within the given functional form. Okay, so this is just a repetition of the thing. Variationally optimized fixed node energy. You can use any orbitals which you want, any one-particle theory or even more complicated. And you get a nice general idea. The variational space is not only the wave function, but also effective Hamiltonian, because it enables you to actually optimize.
This is not completely consistent, because in general, the effective Hamiltonian you use is used in the framework of DFT, essentially, or Fock.
Or, well, here I would...
When you project, you're actually building up correlations that you do not include real theories.
That's exactly right.
Sort of.
But you are always allowed to...
It's an effective Hamiltonian for a QMC calculation, essentially, not in the sense that it's a
right?
No, it's for the trial function.
For the trial wave function.
For the trial wave function, yes.
So basically, you are essentially increasing your variational space in an effective, in a clever way.
Yes.
But, and that is a good point which you mentioned, you can go back. Okay? Now, let's go back. Let's take that Hamiltonian, let's take that effective weight which you found, and let's have a look on a one-particle spectrum what actually that Hamiltonian has. So this is the density of states with various mixing. We saw about 20% was the close to the optimal. You look at the whole thing and you see that the gap is just about right.
What does it mean it's just about? How do we know it's about right? Looking at that only.
Pardon?
Looking at that only, you cannot say that. You see, probably you have some additional information, experiment or something, right?
Well, yes, of course. At the very end, you always compare with experiment. So you say the gap is right when it is really close to experiment. About 3 electron volts plus, yeah.
Okay.
So, but I mean, I would say now that I optimized this in that theory and came back to the effective Hamiltonian, and it looks reasonable. So it says that the Hamiltonian is reasonable, and now we have even reasonable value of that parameter.
On the other hand, not the balance, the excited states, you see, don't count, they don't participate in the Slater determinant. They don't have any information about the excited states.
That's exactly right. So I'm saying, even if I didn't use that information, that effective theory has some reasonable background, because if I plug it in, I get the reasonable spectrum.
No, but that is not an explanation.
It is not an explanation, but...
Wait, because when you do a minimization of the energy by means of a variation or a fixed node calculation, whatever, actually, it's like you built up, I mean, if you expanded your wave function, the wave function that you would get from the fixed node in terms of Slater determinants, that would be a huge combination of Slater determinants. So in principle, you build up the information about the excited states by projecting.
The information about the excited states is included, of course, in an undesirable way, because they simply mix into your trial wave function, whether you like it or not, because it's never exact. Right. But then basically you know about it because you are projecting it out, so in some sense you get some indirect information about it. Can
you say then that if you do, for example, perturbation theory instead of quantum Monte Carlo, second order perturbation theory, you obtain the results about the same accuracy.
That I don't know whether I would get the same accuracy.
Because you see, if you get that, you see the gap, it looks like you see the second order perturbation theory, probably that should give you most of it.
In this case, I
know,
mean, in
I'm
some
asking.
molecular case, maybe. In this case, this is a mod insulator. That's a lot more complicated business. I wouldn't say that the second order perturbation theory would get you in there.
Yeah, because you already fixed the gap, so you have an idea about the residual interaction with respect to the gap. So basically, you should know the weight of the excited states you are going to mix in. So probably that should be a pretty good guess.
I don't know whether I know those weights. That would be pretty
No, but
difficult.
knowing the gap, you see, that fixes the gap, because you have the electron-electron interaction, it's fixed, you don't do anything to it. So that's going to tell you, see the transition. to the
Right.
excited states.
But
So
this
basically
is,
that's the only
you know,
parameter.
my calculation of the gap is different because I really build one state and the other state. But this is coming from something else. This is just the effective one-particle theory from which it comes as an eigenvalue, and it's not. These are not the same things. Anyway, let me continue. So this is going very lively discussions and a pretty long talk. So I start to be worried. So anyway, another example, which I go through it very quickly. And unfortunately, you can't see Matusz here, but he's sitting over there. So this was a work with my collaborators in Slovakia, with Lucia Horvatova, Matusz, and Ivan Stich, which was actually a very cool system, which is vanadium-benzene. Well, you would say, what is so interesting on this thing? You have a benzene and a vanadium atom, 7 heavy atoms and 6 hydrogens. After 80 years of quantum chemistry, one would say we should be able to get this like nothing. The system is actually motivated by spintronic applications, because there was actually thought that this would be something like a spin valve, namely the gap for the spin up and gap for the spin down would be very different, so you would get in different conductivity depending on what would be the spin of the carrier. And actually, it was not clear whether this is high spin or low spin. So we would plug in something in, and these are various functionals which you can use. They have various types of things in them, and you get this picture, okay? You get the relative energy of the possible multiplicities within that system, which is doublet, quartet, or sextet. This is the lowest, and then this one, and then this one by about 0.4 electron volts, and vice versa in various directions, and you can get almost any ordering which you want.
It's like in nuclear physics, more or less.
Okay, so in reality,
You know which one is.
in reality, after Lucia and Matusz did really nice calculations in there, they found the following. All 3 spin states are within 0.1 electron volt. They are almost degenerate.
And this is which spins you're talking about?
This is the spin state of the whole system. The point is that vanadium has an open shell, therefore they could.
How many valence electrons in
In vanadium, you eliminate neon cores, so you have 8 plus 5, 13 valence electrons on vanadium, and then each carbon has 4 valence electrons and hydrogens have 1, so of the order of 30 or 40 electrons. We did the larger calculations, but here the differences were the most dramatic, so it's the most interesting story, I guess. So the states are nearly degenerate. If you actually try to look for the dissociation energies from various theories, they vary between almost very small values up to almost 2 electron volts. The experiments, of course, there is a scatter in the experiments, which is reasonable to expect. In the fixed node diffusion Monte Carlo, basically, we ended up here. Note that we roughly know where it really is, while from these theories, actually, you don't necessarily know. Okay, so let me mention a little bit like a current status of these things. we can do hundreds of valence electrons calculations, and you get these types of results, which is as follows. The agreement with experiments is usually within the few %. And so in some sense, I claim that we cornered the correlation problem, which is exponentially difficult, as we all believe, into the last few percentages of the correlation energy, definitely at least in these types of systems. Sometimes the plain vanilla single determinant nodes are very accurate, and I will elaborate for the rest of the talk when it is the case, when it is not the case, and so on.
Is that predictable?
That's a good question. We are building more and more knowledge to be actually able to reach the point that it's predictable. So far, it has been a posteriori. We basically did, and then we looked, and did, and looked, and iterated until we built a little bit of a knowledge. I'll try actually to build a little bit of the knowledge in the rest of the talk. No ad hoc parameters, no Hubbard stone. It's basically the upper bound method. And this is actually very interesting, and that's the fundamental. Pardon?
You mentioned BCS condensates there, so you said you don't deal with pairing, and now what you're doing there.
Okay, but I mean, with BC condensates, I don't have it in the. Okay, I just mentioned that, and I don't have actually in the talk, although we have papers on it. But here we take that it's something like a unitary ensemble where you have attractive interaction from the very outset.
Yeah, but that's very different from what you talked so far.
That's right. But I mean,
Okay.
I'll be glad to give another talk and show you what we did for BCS condensates. But nevertheless, I just talk about these examples here because of the time constraints. And since I'm roughly at 1/5 of my talk now. But what is actually interesting, and this is a posteriori, is that of the order 90 to 95%, and definitely in many chemical systems we can verify that by alternative method, most of the correlation is actually bosonic-like, namely within the nodal domains. And those things are actually very nicely captured by this methodology. So that's why it works actually so nicely. But we are, of course, not done. There is the fixed node bias. And that is still of a consideration, although for many quantities, definitely if you are looking for the resolution and accuracy of about 0.1 electron volts, you are in a pretty good shape. Cohesion, gaps, optical excitations, all of these quantities you can actually calculate reasonably well. It's not always kind of hand-waving. There's a lot of methodology behind it, but fundamentally it can be done. Now, cons, of course, there are. If you compare it to sophisticated mean fields, such as versions of DFT, QMC is slower by a factor of 1,000 or maybe even 10,000 if you take a particular system. So you get a hit by 1,000 right from the outset. So it has to be a problem which is worth of the investment to do those types of calculations. There is also a fundamental point. 5 to 10% of the correlation is very important if you start to think about the finer energy scales and finer effects. Difference between the two magnetic phases or something like that, where the resolution of 1/10 of an electron volt is not enough. If we would say, coupling with phonons or something like that, resolution, I mean, you need 10 millivolts or better. We are not even close there. Yes?
I go back to this vanadium-benzene.
Mm-hmm.
When you study as a function of the spin multiplicity,
Mm-hmm.
you actually change the nodal structure dramatically by
That's
going
right.
to 2, 4, 6, and so on.
That's right.
But the energy seems almost independent of that. And this is kind of a bit unexpected because the kinetic energy obviously varies a lot because you change the nodal structure. But at the same time, the potential energy probably goes down.
It compensates out,
Yeah,
yes.
So how do you explain that? Because I don't know. Do you have an explanation?
Well, in this case, I say this is what it is. So basically, it compensates.
It looks like you see that the polarized system, it will have the most binding energy according to that. You see, because the binding energy seems to be increasing.
It's increasing by a very little bit. Just a little bit. It's almost on the it's almost on the edge of what we can actually get in there. What you basically one of the points I understand what you're asking. How are you sure that if you change the spin state, the systematic accuracy of the whole thing is actually roughly constant? And you could measure it sort of indirectly and not very precisely if you look at the fluctuations which you get around the eigenvalue which you're getting. Namely, not only the energy, but you look at the fluctuation of the energy. And if the fluctuations of the energy are roughly similar or almost the same, you basically can sort of indirectly claim that the energies, the systematic errors which you're making are probably of the same type. But it's not a perfect justification. The trouble is that the fluctuations are typically much larger than the energy differences between those states, so you do not have a perfectly clean signal there. Yes?
Can you wrap it up in 15 minutes or so?
Really? Okay.
20.
Okay, so I will skip this. I will do a little bit of an education here, which will be very short, but anyway. I mentioned those nodes, and this is not such a well-known topic, so maybe it would be worth to talk about it. Why I'm talking? Well, we know why I'm talking about it, because these are this is the point which actually decides the accuracy of those calculations, and one can build a little bit of an understanding here. So consider a one-dimensional case, and you have something like a function or eigenfunction which is of the nth degree. Then you will find out that it divides the space into n+1 domains. So there is a one-to-one correspondence between excitation and the domain count. For example, this would be the fourth order state, say the polynomial part of the harmonic oscillator state.
But this is only for one dimension.
That's exactly right. So for the larger than one dimension, nth excitation has m or less nodal domains, and that's a famous current thing. For example, I have an example which is exact. So consider two electrons in helium-like atom. So you take 2p square occupation, which is the fifth excited state, but it's the lowest state of its symmetry. It has only two nodal domains. One can prove it exactly. Even with interactions, the symmetry is so high that it actually determines the nodal surface. Qualitatively, basically, the node costs kinetic energy, so the nature wants it to be small. Okay? Namely, it tends to minimize the number of nodal domains and cells when enough space is available and where there are no other constraints. Actually, it is interesting to look at the nodes of excitations, and some famous people were working on this, and one of them proved the following, that the volume of the nodes, Hausdorff volume of the nodes, namely how much of a hypersurface that has, is actually bounded from above and below. So the nodes of highly excited states are actually very nicely behaved. They simply don't grow too fast. They try to be sort of minimal in some sense. You see it dependent on square root of m. So all the node excitations are well behaved. So what else do we know at present? So in one dimension, as I mentioned, if you put fermions on one dimensional line, then each time two fermions cross, you go from one domain to another domain. Since there are n factorial orderings, you have n factorial domains. Now in 3D or 2D, this is not the case. There will be less domains, and in particular for this one, this is also an exact node. For this particular state, you will find out there are only two nodal domains. The node is basically R1 is equal to R2, and you have two domains because you either have R1 larger than R2 or R2 larger than R1. And there is no other possibility. This can be proved exactly. We found actually one 3-electron system where we know the exact node because of restrictions of the symmetry. If you take this interesting state, which is 3 electrons in Coulomb potential, and you take S symmetry, quartet, and odd parity, you get this funny state. It's the lowest state within that symmetry category. You can find that the exact node has this. It looks almost like a parity condition, which it is actually. And there are only 2 nodal domains because those 3 vectors are either left-handed or right-handed. On one side you have plus, on the other side you have minus. Irregardless of the interaction, you can crank up any interactions you want. Symmetry basically is so restrictive here that there are no other possibilities. So there was actually conjecture that the 2 domains is universal for fermion ground states, and David separately played with it for some time. I played with it too, and I will skip this how the sausage is made, but give you this kiddie proof that this is the case. You wouldn't believe that when you were playing in your, in your elementary school with the sliding 15 puzzle, idea of which was that you got this puzzle and here are these squares which could slide and one square was omitted, so you could do these triple exchanges. And if you would get into the first sort of the most ordered permutation, you would end up with something like this. You have an order like in here, and the empty square would be in the lower right corner. Now, you know what has happened. Somebody didn't show you what he did, and he would do this, and he would flip 2 of them using the 3rd dimension, which is forbidden, okay? If you do that, you try to reproduce this as much as you want, you will never ever get there. It's impossible. And the reason why it is impossible is that if you have this type of configuration, or you start from this and you scramble it without using the 3rd dimension, you explore even permutations only. If you flip 2 of them, you go through the forbidden direction, basically you're jumping from one nodal domain to another, then you will explore only odd permutations only, and there is no possibility how to get from here to there using only 2 dimensions in this setting. So in some sense, this is the most interesting and funny example of 15 fermions in 2D with hard cores. There are only 2 nodal domains. Well, this is not the proof, but basically it's a nice mechanical sort of illustration that this is the case. And the fact that here you exhaust permutations of this type and here of that type is actually well known in math. The proof actually took a long time to get. The shortest one is about 5 pages, about 20 years old. Nevertheless, so if we have, basically this was for spin polarized fermions. If I have unpolarized fermions, of course what happens is that I again factorize into spin up and spin down states. And what happens is that if this one, if we believe has only 2 nodal domains and is has 2, of course we will have 4 because it's a direct product of those 2 cases. What happens when you switch the interactions on? Well, what happens is that this nodal domain degeneracy is lifted and you get a topology change and it again fuses into 2 minimal. Let me give you a quick example. You take Hartree-Fock wavefunction of the beryllium atom. Of course, you have the product of these 2 determinants. Hartree-Fock node is given by this product. Now, what it means, electron of a spin-up sees a sphere passing through the other electron with the same spin. And, of course, for the downspin, it's the same thing. So you get 2 concentric spheres. Now, imagine that you actually correlate, that you crank up the interaction and you correlate. The approximate node is given by this equation, and you see those 2 concentric spheres now fuse into one manifold, and you have a hole here, so you can actually get from outside into inside, so to speak. So, and again, there's only 2 nodal domains only. You are either out or in, so to speak. Interestingly enough, the same thing can be found, say, for fully spin polarized, how the interactions actually change it. So if I take Coulomb potential in the lowest quartet, with 3 electrons of S symmetry and even parity, I get this state, 1s, 2s, 3s. It's again the lowest in the symmetry class. When it is non-interacting, it's degenerate with this guy, okay? And if I switch off the interaction, of course, this will split. This is an interesting, sophisticatedly, I played with it a lot to find out that the Hartree-Fock node has 6 nodal domains, okay? It over-compartmentalizes. Why it has 6? Because this is only radially dependent, and therefore it's effectively one-dimensional, so you get 3 factorial, namely 6 domains. If you correlate with the interactions, of course, these are the 6 domains by these equations, well, you will find out that it kind of connects the pluses with the pluses and minuses with the minuses in the other direction. And this seems to be perfectly generic.
Can I turn you back?
Yes.
If I think about spin up and spin down, so this is right. I don't care if the numbers are equal. But if I think of the spin ups, the number of domains have to be even. You see, I think.
Sure.
For the spin down, it has to be even. Now
Sure.
I take the product, that should be divisible by 4. Then 6 is not.
No, in which sense? No, 6 is.
For the spin up, you see the number of domains should be divisible by
Yeah.
2. For spin down, should be divisible by 2. So, but the total weight.
6 is divisible by 2 because 6, they are spin polarized. All 3 of them are up. So I do not have for that state,
You have only
spin up.
polarized. Okay.
It's a quartet. So in that case,
Sorry,
that is
I
not in there.
missed that.
Yeah. So it's a quartet. So in that sense, that the other spin state is not there. That was actually to show that this happens both for spin unpolarized and polarized cases. So you could say the following. We know all bosonic ground states are S waves in its ground state. Fermionic ground states are sort of global P waves in a sense with regard to parity of permutations, not to some particular angular momentum or something like that. Okay, can we learn something about the bias? And this might be interesting too, I haven't shown this before. So again, let's take the beryllium atom. I wanted to know what actually affects the fixed nodal error. So I take beryllium atom since I know essentially I know bad nodal surface and I know essentially exact nodal surface. There's a big actually signal of that error. It's of the order of 10%. So I have either the Hartree-Fock or 2 configuration wave function, and this actually happens to be very accurate. One could check with independent methods, you get about 99.9% of the correlation. That's actually this thing which I showed before. And now let's try to vary the density by increasing the nuclear charge effectively from lithium minus, say, to Z equal 25. And well, does the accuracy still holds? Okay. So this is how it looks like. This is the fixed node error as a function of the nuclear charge. This is for the Hartree-Fock wave function. And you see it goes linearly with Z, which is kind of interesting. If you take those 2 configuration nodes, this is essentially flat, it's 0, and this has been checked by an independent method. Here you can use CI very easily actually to get the exact energies. So the nuclear bias, the fixed node bias is actually sensitive to the electron density. And it goes linearly. One can do the same exercise with the other case, which I mentioned, which were these 3 electrons in the quartet state. And you see here you get actually very bad correlation energies for the Hartree-Fock nodes, because this is actually 7th excited state, so Hartree-Fock doesn't describe that state really very well, although it's the lowest state in its symmetry. And actually, when you take the 2 configuration thing, suddenly you sit on the curve, and it captures almost everything. Not all of it, but almost everything. And again, you see that it has a linear dependency on Z. Okay, now, hour is gone. I'm roughly, but I could do it at other time if you are tired, or I will be glad to follow your instructions.
We can. When are you leaving this week?
I'm staying for the whole week.
We could do a part 2 on this.
If anybody would be interested, I would be more than happy, of course, to continue.
If you have enough for part 2.
I have plenty. I have plenty, and then I just skipped many results actually. So.
I have other things to do. There's a deadline.
Sure.
I have to meet deadlines.
I don't know. I mean, or alternatively, we can go on.
Are you guys planning on doing afternoon discussion sessions?
Yes. No, I didn't mention all that. In fact, that there is also that option.
So one option would be to have part 2 during the afternoon discussion.
You should give a flavor of what.
Yes. Why don't you go quickly through the
Okay.
You say what you did in car.
So
You know
basically,
what
this is going into beyond Slater determinants, and I mentioned BCS wavefunction, and actually a generalization of that is the Pfaffian. So here in the BCS, basically what you have is a determinant of a pairing orbital, and in Pfaffian you can have any spin state, any anti-symmetrized pairs where these are spin orbitals. And the algebra of the Pfaffians, I believe, is known. It's a special determinant is a special case of the Pfaffian, and the algebra is actually similar to determinants. And if you actually write this pair spin orbital and decompose it into space and spin degrees of. Pardon?
What are the
No, just go quickly.
Okay. Less details.
Show us the titles.
So we were able to build this type of a wave function and get these results where you could see difference between Pfaffian and BCS nodes. It's not completely negligible. There is a triplet correlation in there. So this is not that interesting. This is interesting, I believe. Why you have? Let's take first 2 rows and build isoelectronic systems from the first 2 rows. Basically, carbon, under it is silicon, here is nitrogen, under it is phosphorus, and so on. And you look at the fixed node errors. They are isoelectronic because we eliminated the cores. The fixed node error in carbon 2 is 46 millihartries. Fixed node error in silicon is 6 millihartries, 7 times larger. We are talking about very few percentages of the correlation energy. Fixed node error nitrogen versus phosphorus, factor of 4. Nitrogen 2 versus P2, factor of 3. I took more of these systems which are isoelectronic, have the same state, symmetries, bonding patterns, and geometries. And then you look at the differences between the fixed node errors. These are the second row, and these are the first row. You see factors of 2 to 3. Why?
Okay.
So possible reasons, none of these applies. It's the energies are similar. These states, it's just the opposite. ECPs have no fundamental contribution. So where it is? You consider the following atom, harmonic potential or Coulomb. You can write 2 electrons in this sp atom like this, and you look for the node. And note this function RHR, which is ratio of the radial S and P parts. And you find this. If we had a harmonic oscillator that would be all flat, it would be a function like this. If you take phosphorus, which is the second row, it is not completely linear, but it's not too complicated. And here you get a huge maximum. P state goes very deep in the core, although nominally it should be out if you would follow harmonic oscillator ordering of the states. So it is completely different. And what this nonlinearity does is that you get these funny pictures on the nodal surface when you scan it by 1 electron and look what's going on. And not only that, but if you correlate, you go from something which is disconnected to something which is connected. And that is bad. For phosphorus, you don't see that. It actually is the same regardless whether you correlate or not. And if you compare this is exactly the same configurations of electrons in both cases. The nodal surface is completely different. That's maybe the signal that I should stop. So the key effects which influence the whole thing, it's the interplay of density and node nonlinearity. If the nonlinearity is contained in the core, it subtracts, you are perfectly fine. If it goes into the bonding region, you are not perfectly fine. And you will see these effects also in transition metals and F elements throughout the whole thing. And maybe I should stop here. And if anybody wants, I'll be glad to continue in the afternoon.
Thank you. I think we had already a number of questions.